thank you very much for this opportunity. And you were quite right. I was in Harald Weinfuhr's group, did my PhD there. And before that, I got my diploma from the TU in Munich. So I'm actually sort of have loose ties to two members of the Munich Center for Quantum Science and Technology. Yes, and maybe just a few words about this company. This was actually founded in 2005. So it's a bit more than 16 years old now. We are still a very small company, around 10 people at the moment, and we're still based in Munich, although a little bit further in the south now. And we basically have two different, let's say, sets of things we sell. One is, and that's something I'm not going to talk about today, is our sort of tools for research and development. And the other part I'm going to talk about today is our educational products. So we're actually going to talk about two of these educational products, which are both based on entangled photons, so or entangled photon pair sources. Right, so there's this one device that we've been selling for a long time already, is what we call the Entanglement Demonstrator, and this was intended as a lab course teaching product, so to speak. So this was, this is how it's usually used at the moment. So it's used for undergraduate lab courses, and one of the basic things you can do with it is test Bell's inequality, see whether we have entangled photons. Maybe a bit, well, a little bit about the physics. So what we actually have is a pump laser that's around 405 nanometers. And we have a nonlinear crystal. In our case, it's a BBO crystal, a type 1 phase-matched BBO crystal. So that always produces the same polarization photon pairs at its output. And this is obviously not an entangled state yet. So what you have to do, or one of the tricks you can use is, and this is sort of mentioned in this paper I've noted down there, is to use two of these nonlinear crystals, each with sort of orthogonal optical axis, and then you can sort of produce, let's say, horizontally polarized photon pairs in the first crystal and vertically polarized photon pairs in the second crystal. And then you have two more magic crystals, these two, we call them compensation crystals. And if you set them in the right way, then the output of this is not just, either a horizontal photon pair or a vertically polarized photon pair, but you get an entangled state out of this. And this entangled state is one of these Bell states. This is a phi state. So depending on how we set this half-wave plate that's in front of this, in front of all these magic crystals, we can either get the phi plus state, which has this plus in here, or the phi minus state, which has this minus here. And then it's quite simple to get the other two, or one of the other two Bell states from this. It's basically, as you can see, you have to rotate, or let's say this one. If you rotate these two, the second photon by 90 degrees, basically, then you end up with the psi states. So that you can do very simple by adding a half-wave plate in one of the arms, for example. Yeah, so this is basically what both of our products are based on. So spontaneous parametric down conversion source, and this has been mentioned before in some talks. So this is what it actually looks like in the QED case. We have this blue laser here, then we have two lenses here. These are mirrors. This is not a lot. And this is actually these two nonlinear crystals glued together. And these are the two compensation crystals. And this is the half-wave plate that we've taken out in this case. So if we remove it, we only produce like horizontally polarized photon pairs. If we rotate this by 90 degrees and sort of put it into the beam path, then the polarization of the pump beam is rotated by 45 degrees. And then both of the crystals are pumped, and then we get this entangled photon state out of it. You see that this is tilted, this one of these compensation crystals, and this is to set the phase of this this whole state that's coming out in the end. And it's set so that we usually generate a phi plus or a phi minus, depending on how this, which way sort of we put this into the beam. Right. So this blue thing that we've seen before is in here, is below this this white enclosure, and then these photon pairs, they're non-collinear, so they're emitted under an angle from the pump beam. And so one of them is going onto this mirror, possibly into this through this polarizer into single mode fiber, and the other one the same on the other side. So we can remove these polarizers, we can put some more in there, we can put some motorized in there if you want. And then from this, we go into single photon detectors. This is what we see here. So these photon pairs are sort of detected in these single photon detectors. And then we have a bit of electronics and some a touch screen there where you can see how many of these you've generated. We can see how many coincidences we've generated or detected rather. And sort of, for example, turn the laser up or down or whatever. This is all done in this. Then we have a few add-ons, and I will come back to a few of those. So for example, this Hongo Mandel thing I will talk about a little bit, this QKD thing I will talk about a little bit, this Henry-Brown twist setup I won't, and the Michelson setup I won't either. And then we have a very sort of, well, a newer product, which is a bit more fancy, but it's based on the same thing. So we have this we call the Quantenkoffer. It's basically a mobile version of the other thing, and a more sort of versatile thing, because you can set these optical elements where you want. But basically, you have this very similar source down below. It looks a bit more fancy because it's a bit more automated or motorized, and yeah, this is down below, and then we have these what we call periscopes up here, and then you have this whole setup where you can play around with these photon pairs that you've generated down below, and then they're flying over the top here, and then they're going down into the detectors again. And then you have these optical elements that you can put in the beam path and play around with it, and it's a bit more versatile than the QED. Right, so a few of the experiments that we can do. I mean, basically, since it's an entangled photon pair source, you can show that there's entanglement. You can violate Bell's inequality. You can look at the density matrix, for example. You can do sort of heralded single photon experiments with this Michelson thing, for example. You can show that there are heralded single photons with the Henry-Brown and twist setup. You can show Hongo Mandel interference. This is what was supposed to be bold and not the Franzen interference, because I'm going to talk about the Hongo Mandel a bit later. And you can do QKD, which we're going to talk about too a little bit. And hopefully, we've not tried that yet, but it should be possible to do a Bell state measurement on the Quantenkoffer and maybe do some dense coding, which would maybe also fall into this into the topic of this whole workshop. All right, so very briefly, QKD, it's a prepare and measurement scheme in this BB84 scheme. It could also be the BBM, Bennett, Brassard, and Merman scheme, which is very similar but uses entangled photons. And basically, what we do is we have a sort of a pulse source and a sort of weak current pulse source. We use a half-wave plate to set the polarization in one of the 4 states that you need, and then we go over to the receiver end, and we can use a half-wave plate to set the basis polarizing beam splitter to analyze the polarization. But in our case, we usually don't have this polarizing beam splitter case, so we basically take a polarizer instead, and we can analyze all 4 states with this polarizer. And yeah, and then you have to do, I mean, you send a lot of photons from there to there, and then you have to do this classical communication in the end, do the sifting process, and all this stuff in the end. We can do this with the QED. We can also do it with the Quantenkoffer, but with the QED, and it's not a very long quantum channel. There are a few centimeters between this half-wave plate here that sort of it belongs to Alice, and the polarizer that belongs to Bob. And it's even arguable whether there's any sort of distance in between it, because all of the electronics will go into the same device, and the key will sort of be received there somehow, or perceived there. So yeah, this is what sort of the hardware part looks like, and this is what the software part looks like. So if you have the fortunate case where you have this motorized, then you can just say, okay, go with it. And this is sort of the Alice part. Alice sort of has chooses one bit for the basis, one bit for the bit value, and these 2 bits will determine which of the 4 states will be transmitted. And the same thing happens basically on Bob's side, but this is sort of sets the polarizer instead of the half-wave plate at Alice's side. And then the question is the photon being detected in the end or not? Mostly we'll find that it's not going to be detected, but sometimes it is. And then in the next run, it will be checked whether the basis is coinciding or not. And then you can actually have a bit, let's say a raw bit, transmitted, and then you will see that whether there are errors or not. You will sacrifice some of the bits to determine the error, and this is where we usually leave it at. As I said, this is just for educational purposes. Right. The second experiment I'm going to talk about briefly is this Hong-Mandel thing, because that sort of leads over to the Bell state measurement. And the idea is you have 2 indistinguishable photons. I mean, it's usually the test whether your photons are indistinguishable. And this has also been mentioned in at least one talk yesterday. And it's sort of an interference effect. You have these 4 possibilities if you have 2 photons impinging on a beam splitter. So what can happen is that they're both transmitted, they're both reflected, or one of them transmitted, one of them reflected, or vice versa. So these 4 cases you have, and if you do it correctly and these photons are indistinguishable, then these first 2 possibilities should basically get removed, and you will always have these 2 photons exit the beam splitter at the same output port. And how we see this is that we don't see any coincidences anymore, because if both photons are hitting one detector, then we don't see this, and we don't see any coincidences anymore. And this is what we call this Hong-Mandel dip, and this is sort of what it looks like. This is the setup we use with the QED. So this is actually the beam splitter. It's a fiber-based setup, and we sort of change the time that these photons impinge on the beam splitter by moving one of these fiber couplers, fiber collimators. And and this is what you see on this x-axis here. So you sort of delay one photon with respect to the other, and when they're arriving at the same time, then you have this sort of interference, destructive interference effect, and then you don't see any, or hardly any, ideally none, coincidences anymore. And as I said, this should be possible to extend this into a Bell state measurement, at least discriminating one of the 4 Bell states from the other 3. And the problem is we can't do this with this QD, because all of these fibers are polarization maintaining fibers. And while this always sounds so good, polarization maintaining does not mean that all the polarizations are maintained. But we could, in principle, do this with the Quantenkoffer, and we've seen this Hong-Mandel dip with the Quantenkoffer. We just haven't tried whether we can sort of discriminate the different Bell states, and this is not necessarily. I mean, we're not sure that it'll work or not, but that would be quite interesting, because then from this we could probably go on and do a sort of a dense coding a dense coding scheme on the Quantenkoffer, which if we only use sort of discriminate one base state from the others, that would mean that we could exactly transmit one bit with 2 qubits or 1 qubit, whatever that means. And that is not, that doesn't really show the whole idea that well, but it's sort of a basic, it would show that we can at least discriminate one base state from the other and sort of show the first attempt. And then probably it's not that difficult to distinguish the one of the other base states. So we could distinguish 2 base states individually from a set of the other 2 base states. And then we could maybe even show that we can do 1.5 bits with this one photon. So that's something that we haven't tried yet, as I said, but that's what I thought would sort of fit best to this, to your workshop, basically. And with that, I'm, as usual, a little bit too early, but anyway, so thank you very much.
Yeah, thanks, Henning. It's very interesting. I like it that this it seems to be possible to do the dense coding in, in the near future.
We'll see, yeah.
So I have these 2 questions that I ask to everybody, and the first one is, well, you know it is. What do you think is the first technical use case for entanglement-assisted communication networks?
Yeah, I think this has been set similarly to what I'm going to say now. But well, QKD is obviously something that's used, but usually entanglement is not used in there. So, and there are some advantages. Like, for example, one could think about in space, if you have your satellite in space and you don't know whether somebody's tampered with it or not, then this entanglement part could help you there. I don't know whether that's going to be the first one that's really commercially used. Otherwise, it might be the quantum repeater part, because there you definitely need entanglement, and whether it's used sort of as an amplifier or something like that for a QKD, or whether it's used to connect to quantum computers whenever they're ready. I don't know, but that could be something that I could think of.
Thanks. Then the next question, as you know, is what is the current main challenge on the path to realizing one of those 2 options? I mean, maybe just pick the one that bugs you most.
Yeah, well, to be honest, since we're not actively working on this, I don't think my opinion is very useful there. I think there's probably quite a few technical challenges yet, and also probably there's some sort of standardization thing that I could think of. But as I said, since we're not actively doing anything in that direction, I don't think that my opinion is very important here.
Okay, thank you.